Hello, and welcome to the third and final IB Math Speedrun, today with me, Vince. So today, in this speedrun, we're going to be covering the final proof that is covered in the IB HL Math Analysis, and that is proof by induction. Let's jump right in. So, proof by induction is actually has two steps. First is called the basic step, and that's when you prove that for some n, usually n equals 1, some function is true. And then you have the inductive step, where usually you prove that for some n equals k, for the case that n equals k plus 1, like as long as n equals k is true, that n equals k plus 1 is also going to be true. So it's a bit hard to explain without actually having a problem in front of us. So let's put a problem in front of us. So the first problem we're going to cover, I'm going to be doing the even ones today. Use mathematical induction to prove the following statements. First one is 1 squared plus 2 squared plus 3 squared until some n squared is equal to 1/3 times n plus 1 times n plus 1/2. So for our basic step, we need to prove this for n equals 1. So how do we prove this? Well, we need to simply prove that 1 squared is equal to 1/3 times 1 times 1 plus 1 times 1 plus 1/2. And of course, this left-hand side will be equal to 1/3. This right-hand side will be equal to 1/3 times 1 times 2 times 3/2, which of course is equal to 1. So we have 1 equals 1. And so that is our basic step proven. We know this case is completely fine for the case that n equals 1. So next, we're going to move on to the inductive step. So for this, you want to assume that for some number n equals k, the statement is true. So what happens if we put n equals k plus 1? So we know the sum of n equals k, the squares of from 1 until n equals k will be equal to 1/3 times k times k plus 1 times k plus 1/2 will be the sum of those numbers. And so we want to prove that if we add k plus 1 squared to this, then then the right hand side will be equal to this if we substitute n equals k plus 1, which in this case is 1/3 k plus 1 k plus 2 k plus 3/2. So let's see if we are correct. So we'll manipulate this side only. So we have k plus 1 squared. So this is 1/3 times k plus 1 times k plus 1/2 plus k squared. Well, actually, hold on. If we're multiplying k plus 1 squared to this entire thing, then it should mean that, let's do some rearranging so it makes more sense. So we have k plus 1 times 1/3 times k plus 1/2 plus k plus 1. Well, what do we do from here? Let's expand this. So we have obviously k plus 1 still on this side is equal to 1/3 k squared plus 1/6 k plus k plus 1. And that's all equal to, let's factor this back out. So this would be 1/3 k squared plus 7 over 6k plus 1. Which is equal to 1/3 times k squared plus 7 over 6 divided by 1/3 is 7 over 2 k plus 3. And of course, if we factor this, this will be equal to 1/3 times k 7 over 2, 3, this would be 1.5 and 1. 2 over 2, 1.5 is 3 over 2. Did I make a mistake? No, I don't think so. What would this be? I think I'm having a brain fart. This would be equal to Oh, I'm being silly. Why would it be 1? No. Of course it would be 3 over 2, right? So if you factor this, this would be k plus 2 times k plus 3 over 2, I believe. So bringing this k plus 1 back down, we have that this sum is equal to 1/3 times k plus 1 times k plus 2 times k plus 3 over 2. And that's exactly what we needed to prove that it would equal. So if we go all the way back up, well, as you can see, that's what we needed to prove that it would equal. And so since our inductive step is true, and since our basic step is true and our inductive step is true, then because of the principle of mathematical induction, the statement is true for all positive integers. Okay, so let's move on to the next one. Can I clear this? The next question will be jumping every sub-question, of course, that we need to prove that the sum from I is equal to 0 to n of 2 to the I is equal to 2 to the n plus 1 minus 1. Okay, so first let's tackle the basic step. Let's say n is also equal to 0. So 2 to the 0 is equal to 2 to the 0 plus 1 minus 1. This is 1 is equal to 2 minus 1, which is, of course, we know is true. So we have the basic step done. So this holds true when I equals 0. So we need to prove for the inductive step. So if we assume that it's true for any number n, then we know if from I is equal to 0 to n plus 1, 2 to the I, this should be equal to the sum of I to the 0 to the n 2 to the I plus 2 to the n. n plus 1, sorry. I believe. Right. And so, therefore, we need to, oh, sorry, no, yeah, so 2 to the I, n plus 1, I 0, 2 to the I is equal to the same, plus 2 to the n plus 1, right? And so, since we are assuming that this statement is true for this, that this statement up here is true, then we can substitute this into the place here. Oops. And so we have 2 to the n minus 1 plus 2 to the n plus 1 is equal to the sum. Say 2 to the n plus 1. So n plus 1, I equals 0, 2 to the I is equal to this. So this is equal to 2 to the n plus 2 minus 1. And so therefore, we've proved it for the inductive step that because if we assume this is true, then if we add 1 to the number, then it will also hold true still. Since we've proved it for the basic step and we've proved the inductive step, then through mathematical induction, we should have proved this correct. Okay, on to the next one. So we have our next problem is E, so 1 cubed plus 2 cubed plus 3 cubed until n cubed is equal to n squared times n plus 1 squared divided by 4. Okay, so let's prove this for the basic step first. Of course, we want to prove 1 cubed is equal to 1 squared times 1 plus 1 squared divided by 4, which is equal to 1 times 4 over 4, which is equal to 1. So this is fine. So for n is equal to 1, we have proved this statement. Now we need to do our inductive steps. So assuming that this statement is true for all values of n, we want to prove that it's true for the next value of n. So we have n squared, n plus 1 squared over 4, which we assume is going to be correct in that it's the sum of all cubes from 1 to n. And if we add the cube of n plus 1 to this, then this should equal this equation, but if we substitute n plus 1 instead. So n plus 1 times n plus 2 squared divided by 4. And so we need to prove this side equals this side. So let's do some manipulation. If we multiply this by 4, then we can divide this by 4, and so we can add it directly here. So we have n squared. We need to prove that more or less n squared, n plus 1 squared, plus 4 times n plus 1 cubed is equal to n plus 1 times n plus 2 squared. Okay, now let's stick to the left side. So we have n cubed, n to the 4. Is that really n squared? Oh, then this should be squared too. Oops. So we have n to the 4 plus 2n to the 3 plus n squared plus 4n cubed plus 3 times 4, 12n squared plus 12n plus 4 should be equal to this. So let's add up like terms. So we have n to the 4 plus 6n to the cube plus 13n squared plus 12n plus 4 is equal to, should be equal to that. Okay. I do not want to try and factor that into that, so we're going to expand this and see what it gives us. So this would be n squared plus 2n plus 1 times n plus 2 squared, so n squared plus 4n plus 4, and hopefully this should equal, so that's n to the power of 4 plus 4n cubed plus 4n squared plus 2n cubed plus 8n squared plus 8n plus n squared plus 4n plus 4. So that would be equal to n to the 4 plus 6n cubed plus 13n squared plus 8n plus 4 plus 12n plus 4. And so we have proved that the two sides equal each other, as you can see. So as we have proved the inductive step, and we've also proved the basic step to be true, then we know that this theorem holds true for all values of n as long as they're positive. Okay, on to the next one.
Hello, I'm back. Okay, so let's move on to the next question. So the next question is we need to prove that 1 over 1 times 2 plus 1 over 2 times 3 and so on is equal to, until 1 over n times n plus 1 is equal to n over n plus 1. So first let's test this for the base case. When n equals 1, 1 over 1 times 2 should be equal to 1 over 1 plus 1. And of course it is. This is just 1/2 is equal to 1/2. So we've already proved this for our base case. And so now we need to prove this for the inductive step. So what we need to prove for the inductive step is that n over n plus 1, assuming it's true, plus 1 over n plus 1 times n plus 2 is equal to n plus 1, that's supposed to be a 1, n plus 1 divided by n plus 2. Okay. So, I mean, this does not look like that hard of a proof. If we simply multiply this by both sides by n plus 2, we get n times n plus 2 divided by n plus 1 times n plus 2 plus 1, of course. Just combining it into a single fraction should be equal to n plus 1 over n plus 2. So, oh, what's that? So this would be equal to, hold on, did I read this right? Yeah, plus 1 over n plus 1, n plus 2 equals n plus 1 over n plus 2. So what is this? N squared plus 2n, plus 1 of course, divided by n plus 1 times n plus 2 is equal, of course, to n plus 1 squared over n plus 1 times n plus 2. Sorry, let me move that so you can see it. And of course, that will be equal to, if we cancel this out, this will be equal to n plus 1 over n plus 2. And yeah, that's pretty much it. So, yeah, that's it for this problem. We've proved the basic step already. We've proved the inductive step. And so through mathematical induction, this statement should be true. Okay, let's move on to the next one. Oh, it's a note. What is that doing? So we want to prove that 2 to the n plus 2 plus 3 to the 2n plus 1, as long as n is a positive number, is divisible by 7. So, yeah. So let's prove this for the case that n equals 1 first. So 2 to the 3 plus 3 to the 3 is equal to 8 plus 27 is equal to 35, and 35 is divisible by 7. So we've proved the basic step. So since we have proved that, what we want to prove is the inductive step. And we can do that by saying 2 to times. So, okay, let's start first with 2 to the n plus 3 plus 3 to the 2 times n plus 1 is still divisible by 7. And how will we do that? Well, we can say this is 3 to the 2n plus 3. So this will be 2 to the n plus 3 plus 3 to the 2n plus 3 should be divisible by 7. But the thing is, what is this? So, this would be 2 times 2 to the n plus 1, n plus 2, plus 3 times 3 squared times 3 to the 2n plus 1. How do we work around this? So therefore, okay. So I got it. So we can substitute this, say that this is equal to some sort of number. So we have 2, can't draw 2 times 7m, where m is just any number, minus 3 to the 2n plus 1, plus 3 squared times 3 to the 2n plus 1 is equal, and then we have, therefore, 14m. Remember, m is just a number that's divisible by 7, minus 2 times 3 to the 2n plus 1, plus 3 squared, which is 9. I'll change that to 9, times 3 to the 2n plus 1. And, if 9 minus 2 is 7. So it's simply 14m plus 7 times 3 to the 2n plus 1. So we've proved that this new number that we've created is still divisible by 7. We've proved the base step, and we have now proved the inductive step, and so through mathematical induction, this should be true. Okay, I think we are on to the last few problems. So the next problem is for r is equal to 1 to n. We want to prove r times the sum of r times r plus 1 is equal to n over 3 times n plus 1 times n plus 2. Okay, this looks pretty straightforward. So first of all, we want to prove it when r is just equal to 1. We want to prove that 1 times 1 plus 1 is equal to 1 over 3 times 1 plus 1 times 1 plus 2. So of course this is 2 is equal to 1/3 times 2 times 3. So these two cancel out, so we have 2 equals 2, which is true. So we've proved it for the base step. Now, we need to prove the inductive step. So, well, what can we say? We can say that the sum of numbers from r is equal to 1 to n plus 1 is, of course, this is equal to the sum of numbers from r is 1 to n of the same, and then we add, of course, n plus 1, because it's n plus 1 here and then n plus 1 plus 1. So this would be n plus 1 plus 1. But I can't erase. So, but I'm going to simplify this. I'm going to say that it's just n plus 2. And so we can substitute this formula from here down into here. And also we want to substitute it into here so we can prove the inductive step. So this would be saying n plus 1 over 3 times n plus 2 times n plus 3 is equal to n over 3 times n plus 1 times n plus 2 plus n plus 1 plus n plus 2. Yeah? Okay. So, well, I mean, this is, I guess pretty straightforward that if we're adding 1 here, then this would be, actually, I think we need to expand everything first. So, let's factor out n plus 2. So we can say n plus 2 times n over 3 plus n squared over 3 plus n over 3 plus n plus 1. And, so this simplifies to n plus 2 times n squared over 3 plus 4n over 3 plus 1. And of course, this should be equal to n plus 2. What does this simplify into? Let's say 1/3 first, so we can get rid of that. So this is n squared plus 4n plus 3. And of course, that is equal to n plus 3 times n plus 1. And so if we rearrange this a little, we can see that n plus 3 over, n plus 1 over 3 times n plus 2 times n plus 3. Just putting this on there. So And I think that's what we need to prove. So n plus 1 over 3 times n plus 2 times n plus 3. Yeah. So that's exactly what we needed to prove. Since we've proved the inductive step and we've also proved our basic step through mathematical induction, this should be solved. So it's cool. So we're now moving on to the final two problems of today. And so we want to, given the statements below, decide how best to prove or disprove the statement. Use any methods. So we can use direct proof, proof by contradiction, and proof by mathematical induction. So the first one we want to prove is that 4n plus 3 squared minus 4n minus 3 squared is divisible by 12 for all positive integers n. I think this looks like a direct proof, but let's just see, because I just want to expand these two just to make sure. So 4n plus 3 squared minus 4n minus 3 squared is going to be equal to 4n plus 3 plus 4n minus 3 times 4n plus 3 minus 4n plus 3. So that's equal to 8n times 3, which is equal to 24n. Okay, so that was pretty simple already. Since this is equal to 24n, it's always going to be divisible by 12, since 24 is divisible by 12. So that's it. It was a direct proof, pretty straightforward. So let's move on to the next proof. So the next thing we need to prove is 1 cubed, this is C by the way, I'm skipping every other one, plus 3 cubed plus 5 cubed until 2n minus 1 cubed is equal to n squared times 2n squared minus 1. Okay. Let's prove it for 1 first. So just 1 cubed is equal to 1 squared times 2 times 1 squared minus 1. So that's equal to 1 squared times 2 minus 1. So 1 is equal to 1. Pretty simple. Okay, so we've proved it. This is definitely a proof by induction, by the way, if you haven't recognized that. So we've proved it for our basic step, and now we need to get the inductive step. So assuming this is true for some n, we can say that n squared times 2n squared plus minus 1, which is the sum of all of the previous cubes of odd numbers, plus the current, the n plus 1 cube, so 2 times n plus 1 minus 1 cubed, and it should be equal to n plus 1 squared times 2 n plus 1 squared minus 1. So if we can prove that the left side equals the right side, then we have proved the inductive step. So first let's expand this, I guess. So 2n to the 4 minus n squared plus, oh, I have to expand this. Okay, fine. Plus, we can simplify this a little. This is 2n plus 1 cubed. 2n plus 1 cubed. So this will be equal to 8n cubed plus for 12n squared plus 6n plus 1, I believe. So we can combine this all together. So we get 2n to the 4 plus 8n cubed plus 11n squared plus 6n plus 1. And again, we could try and factorize this, but I don't feel like it, so I'm just going to simply expand this side as well. So we have n squared plus 2n plus 1 times 2n squared plus 4n plus 2 minus 1 is 1, so it's that. Yikes, it's not like fun. It's equal to 2 equal to 2n squared plus 2n to the 4 plus 4n cubed plus n squared plus 4n cubed plus 8n squared plus 2n plus 2n squared plus 4n plus 1. 2n squared plus 4n plus 1. So we have 2n to the 4. Yep, 2n to the 4 plus, what is this? 4n cubed plus 4n cubed. So plus 8n cubed. And then n squared plus 8n squared, so it's 9n squared, 11n squared. Plus 11n squared plus, so that's 2n plus 4n, so that's 6n plus 1. And I think that's what we need to prove that it equals. And so we have proved that the two sides, left and right, both equal. So we've proved the basic step and we've proved the inductive step. So through mathematical induction, we've proved that the statement is true. And for our final statement, we need to prove that, where's it gone? We need to prove that n cubed minus n is divisible by 3. For all positive numbers. How would we do this? I mean, induction seems viable, I think. But let's just think. I mean, clearly, when you expand this, you get n times n plus 1 times n minus 1. But where would we go from there? Oh, no, of course. This is just a direct proof. So, because we're getting 3 consecutive numbers, n minus 1, n, and n plus 1, obviously, one of these numbers has to be divisible by 3, because, say, okay, for the case n modulo 3, which is, what's the remainder, is equal to 0, of course it's divisible. For the case that n modulo 3 is equal to 1, so when we divide it by 3, we get a remainder of 1, then n minus 1 will be divisible by 3. And in the case that when we divide it by 3, we get a remainder of 2, then n plus 1 divided by 3 will give a remainder of 0. And so that's pretty much it. So that was the end of today's speedrun, which was day 3. So we have 55 days left to go, I believe. I hope you enjoyed the speedrun. I hope that you're a lot more confident on proofs, because I definitely am right now. And I hope to see you in the next speedrun. Ta-ta!